Bismillahirrahmanirrahim. Assalamu alaikum dear students. I'm Arif and I welcome you all to lecture number 37 on the subject of computer organization and assembly language programming. The title of today's session is Logical Operations. Well, this slide shows the agenda for today's session. We'll start with a quick recap of x86-64 register set, programming toolchain and instruction categories. We will then discuss the logical and, or, not, XOR and test instructions. And finally we will have a working demonstration of these instructions using the GNU GDB debugger on the Linux terminal. So first a quick recap. Well, this slide shows the register set of x86-64 microprocessor, the 16 64-bit general purpose registers, the flag register, the 6 16-bit segment registers, 8 80-bit floating point registers, 16 128 256 or 512 SSE media registers, and finally this 64-bit RIP register containing the logical address of the next instruction to be executed. Also the 40-bit linear view of the physical memory is shown over here. Well, this slide summarizes the x86-64 programming toolchain and the structure or layout of assembly program that we have discussed in detail in probably lecture number 28 and 29 of this course. Well, dear friends, do keep in mind the difference between this 48-bit logical address space of a process with the 40-bit physical address space shown on the previous slide. And this slide shows the categories of x86-64 instructions that we are going to study in this course. We are done with the data transfer and the arithmetic instructions, and today we will start with the bit manipulation instructions, and in this category we will discuss the logical instructions today. My dear students, all logical operations like AND, NOT, OR and so on, they work at bit level, and the result is a Boolean value. A value of 0 is considered false and a value of 1 is considered true. Let us discuss all these operations one by one. The AND instruction is a two-operand instruction that performs a bitwise AND operation on its two operands and stores the result in the first operand as per the Intel syntax. Well, this destination operand can be a register or memory, while this source operand can be a register, memory or an immediate value. However, remember two memory operands cannot be used in one instruction, and both these operands need to be of the same size. Well, the behavior of AND operation is the result bit is 1 if corresponding bits of both these two operands are 1. Otherwise, it is set to 0. Well, after the AND instruction is executed, the overflow and this carry flag, they are cleared. The sign 0 and parity flag are set according to the result, while the auxiliary flag is undefined. As far as the usage of AND instruction is concerned, it is used to clear the specific bits while preserving the others. A 0 mask bit clears the corresponding bits, while a 1 mask bit preserves the corresponding bits. Let us see an example, and suppose that we want to check whether a given number is even or odd, and this can be achieved by ANDing the number with 0, 1. These are the two code snippets that describes this. Over here we have a decimal value 27 in the 8-bit AL register. Binary is shown over here. And once we perform an AND operation of the contents of AL register with 01 hex, we get this value. So since this is an odd number, so you get a 1 as output. On the contrary, over here you can see that since the number inside the AL register is an even number, after we perform an AND operation with the mask of 01 with the contents of AL register, we get a 0. So for an odd number, we get an output of 1, and for an even number, we get an output of 0. So this is how in assembly we can identify whether a number inside a register is even or odd. Let us see another example. And suppose this time the programmer wants to clear the higher order 8 bits of AX register. And this can be achieved by ANDing the number inside the AX register with the mask of 0F hex. So the higher order 4 bits are cleared while the lower order 4 bits are preserved. And the same process can be done with 32-bit as well as 64-bit registers. And this example requires to clear the sign bit of a number while leaving the other bits unchanged. Can you think of a mask that can do this job? Can you try that? Well, yes, you are right. A mask of 7F will do this job. Note this code snippet. After the AND operation, only the sign bit of AL register is cleared. Rest all the bits are preserved. Great. Okay, so this is another example, and in this example the programmer wants to clear the even number bits of a register, leaving the other bits unchanged. So once again, can you think of a mask that can perform this job? Well, yes, you're right. The mask can be AA. This is the code snippet. Note the bits at position 0 is cleared, 2 is already cleared, the bit at position 4 is also cleared, 6 is already cleared over here. So this is how we can use the AND operation to clear out the even number of bits. The same way we can clear out the odd number of bits as well. You can do that at your own. You can think of a mask that can perform that job. Okay, so now let's see if you can do this. Suppose the AL register contains the ASCII code of a lowercase alphabet, and the programmer wants to convert it to uppercase. So this AL contains 61 hex or maybe 97 decimal, and of course you all know that this 97 decimal excuse me, is the ASCII of the lowercase a. And we also know that the ASCII of uppercase A is 65 decimal. Can you think of a mask with which we can AND and convert this ASCII to 65? Well, yes. The mask is DF hex. Note the bit position at 5 having the weight of 32 is 0, rest all are 1s. This bit position is 0. So after the AND operation, the value will be reduced by 32 decimal, which is the ASCII of the corresponding capital alphabet. Keep in mind, dear students, that this can also be done by subtracting 32, but the AND operation is better from performance point of view. Okay, so now suppose a user has pressed or entered the key 2 on the keyboard, 2, and the program will receive the ASCII of that decimal digit 2, which is of course 32 hex or 50 in decimal. So the user has entered a digit 2 and the ASCII is there in AL. The programmer now wants to convert this ASCII value to integer. The same task you might have performed in C or C++ using the A to I function. So the mask to do this job is 0f hex. You can do this with other digits as well to build your confidence. And some of you might say that this can also be achieved by subtracting 48, which is the corresponding ASCII of 0. Well, yes, however, once again, this AND is a faster operation than subtract. Okay, so enough for the AND operation. Let us talk about the bitwise OR operation now. Well, dear friends, the OR instruction is also a 2-operand instruction that performs a bitwise OR operation on its 2 operands and stores the result in the first operand as per the Intel syntax. The destination operand can be a register or memory, while this source operand can be a register, memory or an immediate value. However, once again remember, 2 memory operands cannot be used in one instruction. And of course, both the operands need to be of the same size. Well, dear students, the behavior of OR operation is the result is 0, the resulting bit is 0 if both corresponding bits of the first and the second operand are 0. Otherwise, it is set to 1. And after the OR operation is executed, the overflow and carry flags are cleared. The sign 0 and parity flags are set according to the result, while the auxiliary flag is undefined. As far as the usage of OR instruction is concerned, it is used to set specific bits while preserving the others. A 1 mask bit sets the corresponding bits, while a 0 mask bit preserves the corresponding bit. Let us understand this with the help of an example. And suppose a programmer wants to set the most and the least significant bits of a number while leaving the other bits unchanged. For an 8-bit number, you just need to bitwise OR the number with the 81 hex. And this is the example. So you can see that only the most significant bit and the least significant bit, they are set, and the other bits of this number are unchanged. Okay, so let's see another example. We have already seen that we can convert a lowercase alphabet to uppercase using AND operation, and let us do the reverse over here. That is, convert an uppercase alphabet to lowercase, and for that we can use the OR operation. And for this we just need to set the bit at position 5 having weight 32. The bit at position 5 having weight 32, we need to set it. So the mask for this is 20. So we need to set this bit and we need to leave the rest of the bits unchanged. So 5A is the ASCII of capital Z having a decimal corresponding value of 90D. So we have bitwise ORed it with 20 hex, and we get 122 decimal, which is the corresponding ASCII value of lowercase z. And of course, you can think of that this can be performed by an add operation as well. Please do the math and practice with other values at your own time. Similarly, in this example, the programmer needs to do an integer to ASCII conversion, I to A. We did the ASCII to integer conversion using the AND operation, and this I to A can be performed using the OR operation. The mask is 30 hex, and some of you again will like to add a value of 48 decimal to convert the decimal digits to its corresponding ASCII. That can also be done. However, this OR operation is much faster than that. Please feel free to do these examples at your own with different values to have confidence that this works with all possible values and can easily be used to convert a decimal digit to its corresponding ASCII. Okay, so now let's talk about the NOT operation. Well, this NOT operation is a single operand instruction and performs a bitwise NOT operation on all the bits of its only operand, and of course then stores the result in the same operand. And this only operand can be a register or memory location. And from the example code, the usage of NOT operation is apparent that it is used to perform a ones complement of a number. So you get the ones complement of a number over here. Simple. Okay, let's talk about the two operand XOR instruction that performs a bitwise exclusive OR operation on its two operands and stores the result, of course, in the first operand as per the Intel syntax. The behavior of XOR operation is the result bit is 1 if the corresponding bits of the operands are different, and the result bit is 0 if the corresponding bits of the operands are same. I think we have done this in the previous pre-mid part of the course many a times. Okay, so flags are shown over here, and as far as the usage of XOR instruction is concerned, it is used to complement specific bits while preserving the others. A 1 mask bit complements the corresponding bits while a 0 mask bit preserves. And this code snippets over here clears the entire register bits to 0. And you can see that we have done XOR AL comma AL, so we get a 0 inside AL. So this is the fastest way of doing it. Dear students, you can also achieve this by subtracting the register with itself, or maybe bitwise ending the register with an immediate value of 0. But this XOR is the faster operation. Okay, let's see another example. Dear students, we have seen that we can convert a lowercase alphabet to uppercase by the AND operation with the mask of df hex. That is by clearing the bit at position number 5 having weight of 32. Similarly, we have also seen that we can convert an uppercase alphabet to lowercase by OR operation with a mask of 20 hex, that is by setting the bit at position number 5 having weight of 32. Now if a programmer wants to convert an uppercase to lowercase and vice versa using the same instruction, then he or she can do that using the exclusive OR operation. And see these two code snippets over here. You can do an XOR with 20 hex, the ASCII of capital B, and it is converted to the ASCII of lower b. So the same XOR operation, the same mask is converting a capital B to a lower b, or a uppercase alphabet to a lowercase alphabet. And over here again, the same XOR instruction is converting the lowercase alphabet to uppercase alphabet. That is great. Let us move ahead and talk about the fifth and the last logical instruction that we have to cover today, and that is the test instruction. Well, dear students, the test instruction is quite similar to the AND instruction. The main difference is after performing the bitwise AND of these two operands, the result is discarded. That is, it is not saved in any of the operand. The test instruction is also called a logical compare and is used to test whether the bits of the first operand are having a value of 1 or not. And the mask should contain a 1 in the bit positions to be tested and 0 elsewhere. And let's understand this with the help of an example. Suppose a programmer wants to test if an 8-bit number, suppose, inside this AL register is positive or negative. Can you tell me the mask that he or she should use for this purpose? Well, yes. Since we want to test the most significant bit, so the 8-bit mask is 80 hex. And so after the test instruction, the programmer will see the 0 flag, and if it is set to 1, the number inside the register is positive. You see, this is a positive number, so 0 flag is set. And in case if the 0 flag is clear, that means the number is negative. So I think this makes sense to you all. Let's see another example. To check if a register contains 0, we need to test all the bits. So the mask is simple, that is FF hex. After the test instruction, if the 0 flag is set to 1, that means the number inside the register is 0. And if the 0 flag is reset, that is, it contains 0, that means the number inside the AL register is a non-zero number. And similarly, to check if a register contains an even or odd number, we need to test the least significant bit. So the mask over here is 0. We have tested just the least significant bit. And after the test instruction, if the 0 flag is set to 1, that means the number inside the register is even. And if the 0 flag is 0, that means the number inside the register is odd. And finally, this example, check if a register contains the ASCII of lowercase or uppercase alphabet. Once again, here we need to test the bit number 5 having the weight 32. So the mask is 32 in decimal, and if the 0 flag is again set to 1, the ASCII of the alphabet inside the register is uppercase, otherwise it is lowercase. Okay, so enough of examples. Now this is the time to move on to the Linux terminal and practically see all these instructions in action. Okay, so here is our terminal. Fine. Let me show you the code first. Logical.nesum. Remember, this program file is there in the course Bitbucket repository. You can simply download this file from there, and these are the different instructions. Well commented code. More or less, these are the same instructions that I have shown you on the slides. Let me clear the screen, assemble it with the -G flag, the output file in ELF64 format, logical.nesum. It has generated logical.o file. Let me link logical.o with the name of logical. Let me load this program in quiet mode inside GDB in the text user interface mode. So here we are. Let me put a focus on the command window. Let me put a break at the label start. Let me see the registers as well and set the layout to reds, and let me run. Great. So we have the register window, we have the assembly window, source window, and we have the command window. And we have a break at the first line of the main. Well, dear friends, these are the two instructions that convert lowercase alphabet a inside the AL register to uppercase using the AND instruction. Let me execute it using SI. Note the AL register will now contain 61 in hex, of course, 97, which is the ASCII of the lower A. And after we perform this AND instruction, we will get a 65, decimal 65 inside the AX register, AL register, and that is there. Okay, so remember, you should not confuse this. This RAX is of course 64-bit register, but we are using the lower 8 bits only. And over here, these two instructions convert the ASCII of 50 decimal inside AL register to its corresponding decimal value, which has to be 2, I think. So this move instruction will move 50 inside the AL register, 50 decimal. And then after we perform a AND operation with 0F mask, we will get the decimal value, that is 2. You can see the 2 over here. Please do keep track of the flag registers as well once you execute these instructions step by step to have a clear understanding that whatever I have said on the slides is being mapped while we execute this code. And over here, these two instructions convert uppercase alphabet to lowercase using the OR instruction. So now AL contains 90, which is the ASCII for capital Z. And after we perform the OR operation, it contains 122, which is of course the ASCII for the lower Z. And then these two instructions convert integer to ASCII. So the AL register contains 5, and then we perform the OR operation and it will contain 53, which is of course the ASCII of 5. These two instructions show you the fastest way to clear entire register content using the XOR. Let me move a 64-bit value inside the RAX register. Once we perform an XOR of RAX with RAX, you will note that the register will be set to 0. Great. Okay, dear friends, to check if a number is positive or negative using the test instruction, we have the 80 hex, and since the number is negative, this is a negative number minus 5D. Please don't confuse yourself with this value. Remember, this FB is the 2's complement of 5, and we are going to test it with the mask of 80. And you will check out the 0 flag over here. Right now it is set, but after we execute the test instruction, this will be set to 0. So since it is set to 0, so that means it is a negative number. And over here we are moving a odd number or even number test. We are moving 6 inside the AL register. We have 6 over here. And now I'm going to check out whether this is an even number or odd number. The mask is 0, 1. And since this is an even number, so the 0 flag will be set. Keep a track of these flag register, and it is set. Okay, so that is great. These are some of the examples that I thought appropriate that we should check inside the debugger. Please make changes to this code, add more examples from your side, and have a very clear understanding of all these logical instructions that I have discussed today. Let me press C to continue so that the program exit gracefully using the exit system call. So let me press Q to exit the debugger, and let me fall back to the slides. Dear students, once again, you can download this logical.nesum from the class Bitbucket repository. I strongly recommend that you should make changes and run this program to have a crystal clear understanding of all the bitwise instructions that we have learned today. So that is it for today's session. I hope it was informative for you all. If you have liked it, please subscribe my YouTube channel and share it with your friends. I wish you all the best. Happy learning and Allah Hafiz.